Hey class, welcome back. I hope you all are having a box-worthy day, and we're going to jump in and continue with chapter 3. We're now going to apply the things we just learned about kinematics and motion to things that are moving in more than one dimension. So no longer are we just moving in a straight line horizontally or vertically, but rather now we can have horizontal and vertical motion together, and we'll see how that works. Much of what we're going to see is very similar to the things that we already discussed in the last chapter. For example, let's start by talking about displacement. So before we talked about displacement as being change in x or change in y, your final position minus your initial position. We have the same definition now, only since we know about vectors, we're looking at our displacement as being the the final vector for our position minus the initial vector for our position. So we can have a change in both the x direction and the y direction. As you see here, from this location around the curve into this location, the race car moved forward in the x direction just a little bit and up in the y direction quite a lot. So we have displacement in both, and to help make sense of that, we're going to be using vector notation. So for displacement, you can see here we're going to use delta, the Greek letter for change again, delta r. So how do we define velocity? Well, average velocity is just the change in position over change in time. Same thing from last chapter, right? So we see here, take our change in position or our displacement vector, divide it by our change in time, and that will give us the average velocity. Again, notice the arrows on top of all of these. That means they're vectors. Notice the time, no arrows, because time we do not define as a vector. So the instantaneous velocity, the velocity at one single point in time, you really need calculus to do it properly, but this is not calculus-based physics. So we just say that if you take your change in time and make it super tiny, as it gets closer and closer to zero, then you approach an instantaneous velocity, which is what calculus does using what's known as a derivative. All right, so now that we have both motion in the x and y direction, our overall velocity is going to be defined as the x velocity and the y velocity together, but since we're dealing with a vector, you'll have to do the x component squared plus the y component squared. Some people might ask, hey, where does this come from? It actually just comes from Pythagorean theorem. Let me show you on the board behind me. So you'll see, right, if we had a velocity vector, if we define this as the x and this is y, and we go ahead and graph it, let's say that this is our velocity vector. Well, this side of the triangle down here, that would be your x component, and then its location here in the y direction, that would be your y component. And so if you make a triangle here, you can see you have a right triangle. And so by Pythagorean theorem, the hypotenuse is going to be equal to the square root of the adjacent side squared multiplied by, plus the opposite side squared. Just to remind you, let me show you. So the overall velocity squared equals x squared plus y squared, right? A squared plus b squared equals c squared. That's Pythagorean theorem. And so the same is true here. So if you're wondering where this equation came from, that's where it came from. So we can do the same game with acceleration, which you'll see in a minute. But before we do, I wanted to do a quick check to make sure we can conceptually understand what's going on. Let's say that you have an object that's moving around in a circle. So here's our circle, and an object is tracking along this path. It can either go counterclockwise or clockwise, okay? And we're told here's its velocity. 2 meters per second in the I hat direction. Remember, that's a unit vector representing the x direction. So you have positive 2 meters per second in the x direction, and then a negative 2 meters per second in the y direction. If it's traveling if it's traveling clockwise for part A, where are you at the instant that the velocity equals this value? Weird question, think about it. And then what about if it's going counterclockwise? Okay, both cases, I want you to think about it, maybe make a sketch, pause the video, and then we'll come back and check together. Did you pause? I hope so. So let's go ahead and start. If we're moving clockwise, we're going around this in a clockwise manner, which quadrant are we in? Are you in the first, second, third, or fourth quadrant? Remember that from math class? Okay, so you're going around clockwise, so you have to be at a place where you have positive x velocity but negative y velocity. So if you look, the answer is quadrant 1, because in the first quadrant, if you're going clockwise, you're moving forward in the x and down in the y. So that would be the answer. If you notice the fourth quadrant, that doesn't work because you're going backwards in the y and, backwards in the x and down in the y. So they would both components would have to be negative here. In the third quadrant, you're going backwards in the x, so that would have to be a negative velocity, but up in the y, and that would have to be positive. And then over here in the second quadrant, they would both need to be positive. So the only place where x is positive and y is negative is in the first quadrant. But if you reverse and go counterclockwise, in that case you'd have to be in the third quadrant, where you're moving forward in the x and down in the y. Again, to show you what these vectors would look like, this is kind of what you would see. Notice that the vector looks the same in both cases, it's just at different locations in the circle. So again, you're having positive x, negative y, and that's how you get a vector pointing to the right and down. All right, so as I mentioned, we can move on to define acceleration, which we know now is just change in velocity over change in time. So average acceleration, change in our velocity vector over change in time. To get the instantaneous acceleration at one point, we just take the limit as time approaches 0. And we know, since we have a vector by Pythagorean theorem and my beautiful picture on the board behind us, that its magnitude is the square root of the x component squared plus the y component squared. All right, so now I have a couple kind of tricky questions. These ones really kind of can mess with you. Let's think about, we now have acceleration in 2 dimensions. All right, so I want you to picture a skier. Actually, you don't have to picture. Here's a picture for you. Think about this skier. He's going down a hill and then is going to approach a curve down here and curve and start going up eventually to go off a jump. And we'll look at the jump afterwards. All right, but I want you, points A and point C can be a little weird. Okay, let's ignore those. But at point B, what is the direction of the skier's acceleration? Draw it. What about at point D? What is the direction of the acceleration? E and F. Keeping in mind, acceleration is change in velocity. So how is the skier's velocity changing at each of these different points? Pause it, sketch it, try it out. Okay, are you ready for this? Usually, very few people get all of these right because it's super tricky, but it's a good way to learn from our mistakes. So let's go ahead and jump in. At point B, what direction is the acceleration? Well, at point B, as they're going down the slope, the acceleration should be in the direction he's moving. He's going to be moving faster and in the downward direction. Okay? The velocity vector stays in the same direction the whole time, and it's just speeding up. All right, so this is what you're going to learn, and I'll show you this here in a minute. If you're speeding up or slowing down, your acceleration is just in the direction of your velocity or against it. But in order to turn, you must have acceleration perpendicular to the direction of motion. So again, let's think about this. All right, let's imagine that my pen is moving this way. Okay, if I want it to turn up, I would need an acceleration upward. If I have an acceleration pushing up, it's going to cause it to turn in this manner. Okay? Sorry, this is a Valentine's Day balloon I got from my wife a while ago. It's still blown up, and so it's floating around. She put it over here just to mess with me. But it's a loan that says Happy Valentine's Day. Yeah, I'm weird. Anyway, sorry about that. So again, to turn, you have to have a perpendicular acceleration. If you want to turn up, you need an acceleration. Basically, think of it as pushing it up. If you want to turn down, you need an acceleration pushing it down. If you want to speed up, you need an acceleration in the direction you're moving. And to slow down, you need an acceleration going against the direction of motion to make you slow down. So with that in mind, let's return to this example. So at B, it's only speeding up, not turning, so the acceleration is in the direction of motion. At D, it's still going downhill a little bit, so it's still going to speed up, so it's still going to have a little bit of acceleration downhill, but it's also starting to turn upward, so it would need perpendicular acceleration upward. Maybe I should draw this on the board one more time to really drive this home, okay? So let's get rid of this picture here. Probably I should have used an eraser rather than my hand. Sorry. So here's our path, right? At point D down here, back a little more. At point D, it's speeding up, so it needs some acceleration in this direction, but it's also turning, so it needs acceleration perpendicular as well. And that force causing it to turn, that acceleration causing it to turn is going to be stronger, okay? So your result would be the combination of these two. So again, you have to make a little triangle. The net result would be in this direction where we have a right triangle here, okay? So that's how we get the overall acceleration being up and inward a little bit. Now at the very bottom, you're no longer speeding up or slowing down because you're at the very, very bottom. So in that case, the only thing that's being done is your velocity's turning as you go through the bottom of that kind of parabola shape. And so that's why the acceleration is only in the upward direction. Whereas by the time you get over here, you're now slowing down because you're going uphill. So you have acceleration this direction, but you're also still turning. So you still have a perpendicular acceleration. And so again, if you combine those two, the net acceleration is going to be inward. I didn't draw it quite as pretty as the diagram, but I really hope that helps drive it home. You can see here that, again, at D, it's a little bit forward of the normal. Normal, again, is code word for perpendicular, right? So a little bit forward of the normal because you're speeding up and turning. At E, it's just perpendicular because you're neither speeding up nor slowing down. And then at F, it's behind the normal because you're slowing down and turning. Okay, cool. That was crazy, right? Confusing. Now, let's try again considering this situation. Now the skier is going to go off the jump and be flying through the air, all right? And it's going to be moving at points G, H, and I. Again, draw the direction of the acceleration at each of these points. Pause it, try it out. All right, did you do it? Did you try it out? Let's see. At all three of these points, the acceleration is only straight down. What? Right? You wanted it to be all curved and inward and outward like we saw in the last one. But in this case, as soon as you leave the hill, you no longer have that hill influencing you. The only thing influencing you is the acceleration due to gravity, which is straight down. Now, some of you might argue there'd be air resistance slowing you down and pushing back a little bit. Okay, I'll give that to you. But for now, let's ignore air resistance. And if we do, the acceleration is only straight down. And so what does that mean? That means your x velocity, your horizontal velocity, must be the exact same at each point in time. So your x velocity stays the exact same, and your y velocity is decreasing or changing in the downward direction. That's why you're slowing down on the way up and starting to come back down. Tricky, tricky, huh? It's such a simple example, just a skier going down a hill and off a jump, but really helps drive home the understanding of the direction of acceleration. So again, just keep in mind that acceleration is the change in velocity. So that makes sense both mathematically, but also needs to make sense in terms of what's going on physically in the real world. So again, if your acceleration is only perpendicular to your velocity, that means it's only going to make it change direction. It's not with it or against it. Okay, so it's not going to speed it up or slow it down, but it's only going to make it turn. Now, if you have this sort of setup, since your acceleration is partly forward and partly perpendicular, you would be speeding up and turning. And then down here, you would be, again, slowing down now and still turning. All right, so make sure you understand what acceleration really is and what it means, both graphically, physically, conceptually, and mathematically. It's a surprisingly confusing concept for something that we're so used to talking about and experiencing in day-to-day life. All right, so now that we've got some of the basic conceptual stuff down, let's talk about what we do with this. Well, we get to use our kinematic equations of motion, just like we did before. But check it out. Now, not only do we have our equations of motion in the x direction, but boom, we also have all four of them in the x and the y direction. So we now have actually really 8 equations of motion. We have a whole set of them with all of our x variables and a whole set of them with all of the y variables. And as you look back and forth, what's the one thing that links the x and the y together? Time, right? You need an object to be at a given x location and y location at one point in time, and then maybe it will move to a new location, both x and y, but they'll be at that final location again at the same point in time. So what you're going to be doing is basically everything we just did in chapter 2, same game, but you get to do it twice. I guess that's 4 times. Twice. Once in the x and once in the y. All right? And then you can put them together, connect them using time. That's a lot of what we're going to be practicing in this chapter. So, again, you have everything to describe the x motion. You have everything to describe the y motion, and when you put them together, it gives you the overall picture of the x and the y motion together. All right? So, the reasoning strategy, the problem-solving strategy, very similar to what we've done before. You start with a drawing, making sure you label your x and y axes really clearly. Make sure you know what you call positive and what you call negative. All right? Make your list of all your givens, the things you know and what you're looking for, just like before. But now you have two sets, right? You have all the x variables and all the y variables, and then the time is shared between them. Okay? Once you do that, you can choose which of the equations. Likely you're going to need more than one now, 2, 3, 4, and then you try to solve. If you're lucky, you can solve for variables using just one equation at a time, but as you'll see for sure on some of the homework and other places, you'll have to use multiple equations together to solve for anything because you'll have more unknowns, more than one unknown in each given equation. So you'll have to do some substitution to try to solve. All right, once you're done, check your answers, check your units, make sure everything makes sense, and hopefully you'll have a box-worthy solution. All right, so I want to just do one quick example with you all, and then we will continue this in the second half of the video where we jump into projectile motion as a whole nother category of problems. So here we have a spacecraft. We're given initial velocity and acceleration in the x direction. We're given those in the y direction as well. Probably I should have explicitly stated this, but if you notice, there's an initial velocity and then I just give you the acceleration. So when you're just given an acceleration like that, we're going to make the assumption that it's a constant acceleration so our equations of motion work. Okay, so we're given a constant x acceleration, 24 meters per second squared, a constant y acceleration of 12 meters per second squared, x and y initial velocities, and we're told that the spacecraft is going to move for 7 seconds. After those 7 seconds, what's its final x and y position, what's its final x and y velocity, and what's the overall final velocity of the spaceship. Okay, pause it, try it, giddy up. Okay, hopefully you did that. The first thing you hopefully did was draw a picture, or you use the picture that I already gave you. Next, you want to label your variables. So here's my x variables. I'm given my acceleration and initial velocity and time. I went ahead and defined my starting location as 0. We get to make up our x and y axes, right? So I'm going to start it at 0. I don't know x final or v final in the x direction, and my variables in the y look very similar with slightly different values. Okay, now we try to solve. We want initially to find x final and v final in the x direction, so it becomes pretty straightforward. I use the second equation of motion, plug and chug, and I find that my final x position was 740 meters. I do the same thing with the first equation of motion for velocity and find that it's increased to quite a rapid pace of 190 meters per second. Both of those, boom, box-worthy. I do the same game in the y direction using the same equations of motion and again get two box-worthy answers of 390 meters and 980 meters. Quick question, what's the overall distance covered? I didn't ask you that, but is your overall distance, let's see, is it just 740 plus 390? No, it's not, right? That's the vertical and horizontal changes, but again, because of vectors, you would have to use Pythagorean theorem to figure it out. The same is also true of your final velocity. It asks in part C, what's the overall final velocity? Well, it's not just 98 plus 190. Instead, it's using Pythagorean theorem, the vector sum of those two components, which should come out to be equal to 210 meters per second. Some of you might have got that, boxed it up, said, boom, done, piece of cake, box-worthy, see you later. But no, that's not it. That's just the magnitude. I asked you for the final velocity. You need to tell me all the information, magnitude and direction. Oh yeah, it's a vector, magnitude and direction. So that's the magnitude, and then you need the direction, and so you solve for the angle theta, and so the magnitude is 210 meters per second, and the direction is 27 degrees above the positive x-axis. All right, so there's one example for you. You'll see others, and you'll get to practice this a lot on your own. We'll go ahead, stop the video here, and then we'll continue with projectile motion in the next video to wrap up Chapter 3. Hope you're having a box-worthy day. Let me know if you have any questions.